Yes.
Before we get knee deep in it, I want to ask you guys, how many of you guys have ever baked a cake?
What was the question?
Baked a cake. Like from a box? Anybody bake a cake from a box before?
Yeah.
Me.
Okay. Everyone? Would I say
Yeah.
everyone in here?
Yes. Yeah.
Anybody not bake a cake before? Okay. I guess I heard one person that they haven't. She sounds like she's about 2-ish, but I don't know.
I haven't baked a cake before.
Okay. Who said that?
Me, Pedro. I haven't.
Pedro? Excellent. Yeah. Pedro's going to be baking cake for us.
I baked cake before.
Yeah, he changed his mind now.
Yeah.
Oh, okay. I see how it is. Okay, so now when you bake a cake, can you guys give me the ingredients to a cake?
Oil.
Yeah.
We have oil. So I like to use butter. So do you mind if I just put butter down?
I said oil intentionally.
You said oil intentionally?
Because I know you like butter.
You did that on purpose. You're hating on me. I see how it is. So I'm just gonna put butter because we're baking a cake for me.
Oh, okay.
Okay. So butter. What else?
Eggs.
Batter.
Sugar.
You said sugar?
Flour.
Meal.
Okay. So let me give you a hint. I'm lazy, so I'm gonna bake it from a box. Okay. So do we add extra sugar to our thing or do we not?
No.
Okay, so we're gonna take the sugar out. So we're just gonna say that batter, right? Or we'll say cake mix, right? Is there anything else?
Milk or water?
Milk or water. Well, we gotta put milk in it, right? It has to have the dairy, Couldn't get away with the oil. How can we not get away with the milk? Okay, so now on the box, you guys, some of you guys are really good at this, right? And you guys kind of know it by the top of your head. How much butter do I add?
A cube.
A cube?
Half a
So
cup.
that's about what? Half a cup of butter?
Yeah.
Or a fourth of a cup? I think you're talking about one of the sticks. Is that what you're saying?
Yeah. Yeah.
So I think that's a fourth of a cup. Okay. How many eggs?
2.
2 eggs? Well, if they're really big eggs, they're 2. And then I've seen some where they're saying a medium-sized egg, 3. So we'll say 2. 2 big eggs.
They're organic.
And how many cake mixes?
One box.
Okay. And how much milk?
A fourth a cup?
A fourth a cup. We're not putting water in there. We got to put milk in it. Come on. I'm fat for a reason.
Y'all know how to cook.
Bake. It's different.
Okay. And that's going to make 1 cake, right?
Hopefully.
Okay, so I'm going to ask you guys a hard question. Now, if I put a minus here, if I take away 1 egg, is my cake going to be okay?
It'll be all right.
Are you sure?
I don't think so.
I think it'll be okay.
Gonna come
Is
out
it going to taste all right? We want, now remember, I have high quality in terms of cake.
Nate said he's had worse, so we could try and see.
Okay, so we'll do this. If I take away the box mix, is my cake going to taste all right?
No.
Okay, so now when we're talking about chemical equations, I saw some crazy things, right? I saw people saying -1 into O4, right? Yields, and let's say, we're going to say 2. Can you guys put yourself on mute if that's, thank you.
I'm of those people, Dr. Henry, because I stopped halfway for some reason when I redid my work.
Ah,
I
you-
realized my error.
oh, okay. So when we're talking about chemical equations, right, we know that we're not going to have a negative of anything, right? So that is the first thing. I mean, so we want to start thinking about this logically. You guys are, whether you recognize it or not, you guys have been doing chemistry since you were like, when you were first able to get into the kitchen. How many of you guys make the little quesadillas, the little cheese quesadillas? You get in the microwave, you climb up and you put in the, do you guys do that?
Yeah,
Yes.
I have a quesadilla maker.
Oh, I'm sorry. I don't have a quesadilla maker. I had to do it the old fashioned way. So,
Actually, I didn't do the negative one though, but I did do the math a little wrong, but I didn't go negative route.
okay. And the other thing is that we want to start thinking about it logically, right? So things that don't make sense, right? You don't want to just put something up there because, to put something up there, we want to think about it. We want to, okay, so does that make sense that I don't have anything or I don't have, so does that make sense? Do you guys understand
Yeah.
where I'm going with this? Okay, so we want to sit there and we want to start setting up the equations so that they kind of make sense to us, right? And if we think of it, you guys all know how to make a cake. That's a recipe. That's a chemical equation, right? Is it not? Yeah,
It is.
no, it is. Good. I'm glad that you guys see it that way
Mhm.
because it's going to make things a little bit easier for us to start understanding it later on when we start talking about how we kind of account for everything. But the first thing that we have to do is be able to balance. Right? So let's go ahead and work with this chemical equation. It's an easy one, right?
Right. Put a 2 in
So,
front of the O2.
well, no, let's start simple, right? So we
Mhm.
want to keep track of everything. And some of you guys are a little bit further along than others. Some of you guys, we kind of left you guys at the beginning. And part of the reason why we left you guys at the beginning, there's two reasons. One thing, you don't talk up. You don't let me know where you're at. That's one. The other thing is that you're not visiting me in my office hours to talk to me about I can't do chemical equations, or you're not visiting the tutors. You saw we had a tutor here. He came in on his own time to help us out. So make use of that time, utilize him. If you're having those trouble, you want to make use of that, okay? And then some of you guys are the talkers, right? Heather, sorry, I'm gonna call you out. Heather's a talker. She loves to talk, right? And she's comfortable. I want all of you guys to be comfortable, even if you don't understand it, because if you don't understand, there's probably at least 10 to 15 to 100 other people who don't understand as well. Okay. Now, the thing is about asking questions. I don't mind answering questions. And if you guys noticed, I will answer them over and over and over and over and over and over again. Have you guys noticed that?
I've noticed.
How many of you guys went to my the lab sessions where we were talking about how to calculate energy?
I go to almost all the sessions.
Okay. So that should tell you if I'm patient enough to answer the same question at least 50 times, because people only listen when they're being talked to, which we want to try to break that habit as well too. We want to be able to listen at all points, because we can learn just as much by watching somebody else make a mistake than us making a mistake. Didn't your mama used to teach you that, or your parents used to teach you that? My mom would always tell me, she'd always says, I don't want you to make the same mistakes that I make, right? That's what she would tell me, right? And so I learned, okay, so let me look first. And then if I still didn't get it, I'm like, okay, wait a minute, hold on. So can you go back just a little bit right there? And even if it was somebody else's problem, right? I'm looking because it can pertain to me. And whether you guys recognize it or not, all of this chemistry pertains to you, right? And so I want you guys to keep an open mind and be willing to take in information. How many of you guys, and I'm just curious, how many of you guys came in and you're like, this is like the last class that you have to take to get into your program? You just got to get this one checked off.
Not the last, one of them.
It's one of the many, but you came in and you had that mentality was, oh, God, I have to take chemistry.
Yeah,
True.
that was me.
Okay.
That was me too.
Okay. So you already came in with a bias, right? Is that
Pretty
true?
much. Yeah.
So you're already hating on chemistry. You haven't even given it a chance.
Well, I took chemistry in high school. I just needed it because to graduate, just to have my degree. I mean, I'm not
Ah,
even in the medical. I'm not doing anything in medicine. I'm a music major.
you're a
I just
music
need it.
major, but
Yeah,
you
I just
still
need
need
it.
it for your degree, and you kind of came
Yeah.
in, God, I have to take chemistry, right?
Right. Yeah. Same
Right.
thing with something with other classes like communications and stuff.
Yeah. Yeah. So you already came in and you're already setting yourself up. So you're already cutting yourself off from learning, right? So you came in, you're like, I want to learn. Damn, I just got to get this checked off, right? So that's also the wrong mentality to come in, right? You want to come in and you want to be like a sponge. You want to absorb, right? And you also want to participate and you want to do, right? So I give you guys a lot of problems, a lot of the things you guys are going to run into and you're going to continue to run into. You may not run into that exact same question, but you're going to run into that big concept, that big idea. And so you need to be able to sit there and apply it to other cases. And what I'm saying is that we're struggling with that application, right? You learn, in theory, you're learning a concept, but we're not applying that concept. You know what I'm saying?
Yeah, it's because people aren't thinking on a particular level.
Yeah. And partially is because we set up that innate bias that, oh, I can't learn it. Or you say, I can't do this. How many of you guys says, oh, I'm just going to fail? How many said that?
I say that like once a day.
You say it once a day?
Through my head a few times.
Every time I open
I
the
never
home.
say that. I'm a winner.
You're a winner? Okay. so
You're
those who are coming in with that mentality, right? Oh, I'm going to fail, right? You've already thrown in the towel, you know? It's like, well, why come to class? You already said you're going to fail, right? Why do homework? You already said you're going to fail. But I'm not saying not to do homework. What I'm saying is that if you come in with that mentality, if you come in with that concept that you're already going to fail, guess what you're going to do? 9 times out of 10, you're going to fail because you've already set up your mind to sit there and say you're not capable of it. Now, I'm going to tell you something. I don't know if your parents have ever told you this, but I'm going to tell you this. You are capable of learning just about anything. The human mind is incredible. And then when you guys let yourself open up, and also if you put your mind to it and you put in the effort, you can accomplish just about anything, right? But it's a matter of what is it that you want to accomplish? Do you want to pass this class? Do you want to get that A? Or do you want to just go through the motions? So, as I said, I went through 60% of the exams already. I have about 40% of them to go through, right? And I'm looking at them. Of the 60%, I'm going to say about maybe 40 to 50% of them didn't even answer questions, didn't even attempt them. Guess what you get when you don't attempt a question, even write anything down?
Get an F.
Right? That's a 0, right? If you don't write anything down, that's a guaranteed 0. So the one thing that I learned throughout anything, right? If there's no points being taken away from getting the wrong answer, right? Then I'm going to put as much stuff as I could possibly think. And you know, there are some people who did that. There are some people who clearly didn't have an understanding of the material, right? And they put stuff, right? You know, but at least they put something. They made that attempt. If you leave it blank, you're setting yourself up for failing, right? At least make the attempt. And believe it or not, sometimes if you go back, like what I would do is sometimes I'd look at another question. I'm like, you know, that question kind of sounds a little bit like what I'm doing right here. Maybe if I go back and look at that, it'll help me out, right? It'll give me something that can help me trigger something, help me remember stuff. Because a lot of times what it is that we bank it, we put it back in the vault in our head, and we just need something to kind of help us get over that hump, to help us remember. Okay? Are you guys with me? Do you understand what I'm saying, or am I just talking?
No, I understand.
I understand.
Okay.
I understand.
So don't leave anything blank. Yeah, it's more work for me, but my job is to actually grade the stuff, right? That's part of my job. So I will grade it. You know, try to help yourself as much as you could possibly help yourself, right? Go back, look at some of the questions. You know, how many people, I was looking at also the times that you guys were taking. Most of you guys finished it in an hour and 15. There are only a few of you guys that took the whole 2-hour time. Is that true?
True.
I took the whole 2.
Same.
I'm going to be honest, Dr. Henry. I accidentally missed one chemical equation. That's why I ended up getting a 0 on 1 because I accidentally missed it.
Okay.
Just one, huh?
1. Yeah. I attempted the rest of them. It's just I missed one. I didn't do anything to it, so
Yeah.
I didn't know.
And so we want to make sure that we want to go back over. And the last thing, very last thing that you do before you hit that submit button, I have to learn this a lot because I'm really quick to hit submit. Because you're like, you've been working and you're like, okay, God, I'm done. And you naturally hit submit and you're like, damn it, oh my God, I just remembered something.
That's what I learned.
So take a moment, take a breather, and then go back and look over and make sure you got everything answered, right? And then again, when you're starting to look over, you're like, oh yeah, wait, I remember this now, and then you'll be able to sit there and maybe get a couple of extra points, right? It's about getting those points, right? In life, it's really about kind of like getting those points too, right? Nobody's going to give you anything, right? I'm not going to give you an A. I'm not going to give you an F. What you get is what you've earned, right? And if you don't do anything, guess what?
You don't get anything.
You don't get anything, right? Right? And does that make sense?
Yeah, no cake.
No cake, exactly. I want cake, yes.
No
Full
piece of
circle.
cake.
So some of you guys could have done better, and it's clear that you guys could have done better. And there's like moments of genius, I'm like, man, that was pretty incredible how they got to that. And you can see it like when I look over your work and I'm like, that is genius, but like there's something that went wrong towards the end. Like you didn't do that conversion, deciliters compared to liters, you didn't do that part of it. So that kind of threw it off. Or, so, you're some of you guys have those glimpses, right? And we want to keep those glimpses. We want to keep them going. And we want them to grow and to grow. So don't give up. Don't leave anything blank. And don't be intimidated, as Nate was saying. Don't be intimidated about the dang proctorial program, right? It's a pain in the butt, but hey, we need something, right? Okay, so are you guys with me on this?
Yes.
Okay, good. Okay, so now let's see if we can get this problem, right? And we want to think about it. Think about it logically, because we've been through this and we can do this, right? And I want some other people who don't normally talk, I want you guys to talk. If you don't get it, say it, right? Because you're not the only one. Based upon your exam, believe me, you are not the only one who are not grasping the material. But you need to step up. You need to start speaking. Otherwise, the ones that do grasp it are just going to keep leading the way, okay? So what would be the very first thing that we want to do? So I wrote down the elements or the atoms that are going to be in this chemical equation. This is an easy one, I know, but we're going to do this. And then I'm going to throw a heart on it. Okay?
So 2 on both sides.
Okay. So we have 2 nitrogens on both sides. So on the reactant side and the product side.
We have 4
Okay.
on the reactant side for oxygen.
So we got 4 on the reactant side, and then how many on the product side?
2 on the product
2.
side.
Okay. Okay. Is it balanced?
No,
No.
it's not.
So I'm going to ask you a question here, right? And I saw this done. Somebody said, okay, so this is what I'm going to do. I'm just going to add a +2 here, and then I'm going to say it's balanced. Is that how we do it?
No.
No.
No, no, because we have to sit there and put a coefficient in front of
Oh,
whatever
true.
we're talking about, right? So what would be the coefficient that would go in front of the oxygen?
The 2.
Dose.
Okay, so 2 times 2 is what?
4.
4.
Okay, so we want to make sure that we're accounting for everything. We're not just putting numbers to sit there and say, okay, yeah, it needs 2. Yeah, we know that, but how are we going to get those 2, right? You can't just add, the rule is, you can't just say, okay, I'm just going to add a special oxygen over here and make it that way, right? We're going to play with the coefficients. We have to play with the coefficients to try to get it to balance out. And so this is multiplication. It won't be an addition part. Does that make sense?
Yes.
Yeah.
Okay. So let's do something a little more challenging, kind of like what we had on the exam. Let's see. So I can't remember the exam question now. Okay, so let's do this. We'll do.
Dr. Henry.
Yep.
The first compound that has N in 2 different spaces, is that right?
Yep, it does.
Okay. I'm not going crazy. Cool.
We'll be talking about that here when we start talking about ionic compounds or polyatomic ions. Oops. Okay. Okay, so let's say we have this guy. First thing that we're going to do.
Write down your elements so you can put the elements from the product and the reactant side.
Okay. So we have N, O, and H. Okay.
There's 2 nitrogen on the product side.
Okay. On the product side. Okay. And then how many on the reactant side?
2.
2.
2 as well.
Okay. Oxygens?
Or on the reactant.
Okay. And on the product?
3.
3.
And hydrogens?
4 on the reactant
4.
and 2.
Okay. Is it balanced?
No.
No.
No, this isn't balanced. It's going to be a nasty one though. Okay, so let's try to figure
Yeah,
out.
that's okay, because when that having that 3, I think, and I'll only speak for myself, having that 3 on the test, I feel like is what made me feel like I had to keep going and going and going, because I would get to a, I don't know, like say even number, but then next thing you know, everything had to go back to odd, even because of that 3.
Okay.
So is there like a trick for that? Is there a trick for that?
Yeah, well, there is a trick, because you know that this oxygen is all by itself, right? This is a loner, right? And so that kind of gives us a little leeway with it, right? It's a loner. So we know that we can use that half type of formula to kind of account for things, right? Even though that it's O2, it's still a loner by itself. So we want to kind of save that to the end, right? To kind of account for everything else. So we want to try to get everything else accounted for. And then we're going to use that last oxygen to sit there and count for the rest, because it's all by itself. Does that make sense?
Yeah. So start with a 2 then for H2O.
Okay. So we'd start off with the 2 for the H2O. Okay. So then that gives me how many now?
4.
4.
And What about the oxygen?
Four.
Five.
Oh, it gives me 4.
4.
So this one all worked out nicely, right? Wasn't too bad.
That's balanced.
Okay. So in this case, this guy's balanced. This is very similar to the one that you guys had on the exam, which was only thing different was.
Yeah, I definitely made this way harder on the.
Yeah. Yeah, same way.
Okay. Simple, not too hard.
Try another one.
Can we try another one? Yeah, we can try another. Let's see, let's do. Let's see. Let's see, hold on, let me make sure I'm thinking about this right. C3H2. Let me draw it out. Okay, so we have okay.
Not okay.
Not okay. Oops, sorry.
Looks like fun.
There we go. Okay, so what's the first step?
Writing our element.
Yep.
Okay. How many carbons?
3.
3.
And on the product side?
1.
How many hydrogens?
5.
6.
Oh, 6.
And on the product side?
2.
And how many oxygens?
3.
And product side?
3.
Okay, so what am I gonna do now?
Mess with the carbon first on the product side.
Okay,
With the CO2.
okay, so what are we gonna do to mess with it?
It has to be 3, right?
Okay. So then how many oxygens do I have now?
7.
7.
Okay. Is that balanced?
No. So would you just jump in adding, do 7 on the reactant side, just since it's, you have to be something over 7? So could you start
Well,
with 7?
I wouldn't. I would actually try to get the other ones because again, this guy is flexible. We're gonna try to save this guy to the end, right? So you want to do the ones that aren't as flexible, right?
You balance the hydrogens
3 and
with the
H2O.
react the product side. I mean,
So
three
the
and
hydrogens.
H2O.
Okay, so how many should I have?
3 coefficient of 3. Yeah.
Okay.
That'll give you
So
6
then
hydrogen and
that gives me,
6.
okay,
and
so then that's how many?
9 oxygen.
Okay,
And then since that O2 is by itself, 4 times 2 is 8 plus that 1 on the first reactant side gives you 9 oxygen as well. So on
okay,
the O2 would be a 4. So it gives you 8 with that single hydrogen in the other compound equals 9.
okay. Did you guys get that?
Let's slow back by 2 steps.
Okay, so,
Just took off like a
So-
rocket ship.
okay, so what he did, he took care of the hydrogen, right? Because again, that oxygen here, this guy is all by itself. So that guy's going to be a little more flexible than others, right? So since it's flexible, we want to save that guy for the very end. And we want to try to get everybody else balanced. So we wanted to get that carbon balance and we wanted to get the hydrogen balanced, right? And that's essentially what he did. He balanced the hydrogens, right? And then that gave me nine oxygens. So I have 9 oxygens to work with, right? But in my compound right here, how many oxygens are in my compound? In this compound?
1.
1. So that means that we have to account for that 1 in there. So if I subtract that 1 from it, then how many am I left with?
8.
8. And then, so this guy, I just got to set it up so I end up with 8, right? So you put a coefficient of 4 in front of it. 4 times 2 is 8, plus 1 is 9. That accounts for all my oxygens.
So was the answer on the test like this short?
What was that?
The answer on the test, was it about like this short as far as like, or I'm sorry, not short, but small coefficient numbers like this?
There's one that was 25.
I was about to say, I feel like I was.
Yeah, because I kept going. I was definitely way over these smaller numbers.
Yeah, there's one that was 25. Yeah. So, I gave you one that was kind of like, okay, so I was building you up. I gave you one that wasn't so hard. Then I gave you one that was a little bit harder. And I gave you one that was a little bit harder. And then, and it's funny, what I saw was, and it sounds weird, a lot of you guys got the one that was the harder one, correct? But you made mistakes on the ones that were a little bit easier.
Overthinking.
Yeah.
On the test, I remember there was ones with like parentheses and like different stuff like that that I hadn't seen before the test. So I didn't.
So do you want to do one for parentheses?
Yeah, that would, because I didn't, honestly, I wasn't really ready for those when it saw the test, so I wasn't sure exactly how to treat them.
Okay.
I mean, I figured out you probably just treat it like a math equation, right? Where you,
That is correct. Yeah.
yeah, everything outside the parentheses goes to everything inside the parentheses. I forget the word for it, but. Distribute, that's the word.
Okay. Okay, so we have this reaction.
Dr. Henry, on the right side,
Mhm.
is that a PO3 or something else?
That's a PO3. Yes, PO3. So you're saying right here,
No, the other side.
over here.
Yeah.
So that's a PO, and then capital P, capital O, 3.
So what does the little O stand for?
So look on your periodic table.
Hmm. Oh, okay.
Do you see it?
Yeah.
Okay. So I kind of threw that one in there because I wanted you to ask just that question. So what is it?
Polonium?
Okay. Okay, so we know that it's a chemical called polonium, right?
Yeah.
Okay, so here we only have one set of parentheses, right? And this basically means that we have two of these guys in this ionic compound. And then they're going to be interacting with a total of 3 magnesiums. Right. So when we have a subscript next to a parentheses, it makes reference to that entire thing that's inside the parentheses. Where if we have a subscript next to an atom, then we know it makes reference to only that atom. Does that make sense?
Dr. Henry, I have a question. Can we
Yep.
multiply like the subscripts? So we would have 6 of PO.
Yes, but you don't want to write it as, so altogether, yes, you'll have total, you have 6 oxygens, but you never want to write it as P2O6 because these guys are not equal. They're not the same thing.
Okay.
They're not the same thing, right?
Okay.
Because this guy says that you have one compound that has all of these guys together, and so they're going to make a certain structure. This guy is saying that we have 2 independent PO structures. Do you see the difference? So let me give you an example. This guy is saying something like this. So if we draw a structure, which we'll be drawing here in a second, it would have oops. Where this guy is like this. Okay.
So the PO3 parenthesis 2 is like saying 2 of PO3.
That's right. Yeah.
Like if you put them in parentheses next to each other and multiply them together.
That's right. Yeah.
Right.
Okay. Okay, so there's 2 ways that we can go about doing this. Well, there's a couple ways that we can go about doing it, but 2 ways that I've taught you guys. Can anybody remember the 2 ways?
The first way is if you see a compound on both sides of the equation, you can just count that instead of listing the elements separately.
Okay. So since these guys are traveling in pairs, this guy Isn't PO3 the same thing as PO3?
Yes.
Okay, so then I can just write PO3 over here. And isn't PO just PO over here?
Yes.
And isn't Mg just Mg?
Yes.
You wouldn't put Mg and Cl together as a compound since it's a compound on the reactant side?
But is it traveling? Do you see it together over here?
The Mg and the Cl, no.
No, right? Because
But
they're
I-
traveling. You want to travel. It's units that are traveling independent. So over here, you just have Mg by itself, right?
Right.
And then you have the PO3 by itself. Here you have the Mg, and then you have the PO3 over here.
So it doesn't matter if the PO3 is together on the reactant side because it didn't travel that way. It traveled separately from the product side.
Okay,
So-
so remember, why would I now think about it? I want you to think about this, Nate. So why would I put POCl3 on the other side if the whole purpose of a reaction is something is changing, right?
Right.
Right. So if I'm just putting it back together, why would that? Does that make sense for me to sit there and write it as putting back together?
No, I guess what I'm saying is when you took PO3 away from PO on the reactant side, like you separated it.
Yeah.
But you can do that for the reactant side, but not for the product side, right?
No, you can do it from. So what we're doing here, we're separating it down here as a unit that is traveling kind of together, right? So
Right.
PO3, rather than just breaking this down to each individual element, instead of just saying PO, PO,
Okay.
Mg, I'm breaking it down as units that are traveling together. These guys are exactly the same thing on both sides. They're traveling together. They're traveling together. You're not losing one to some other compound.
Right, but what I'm saying is so like PO3
Uh-huh.
is together, but magnesium is 3 on one side and none on the other side.
Okay, but the PO3 is 2 on one side and 1 on the other side.
Right. But the base compound, that PO3 is the same on both sides?
It's the same thing. It's saying, okay, so for instance, I'm saying like this is X. So we're going to say PO3 is equal to X. Okay.
Right.
And then all I'm saying is that all this is Mg 3 X 2, right? And then if I go to the other side, I have PO X.
No, I
Okay.
understand that. I guess what I'm saying is that PO3 has that 3 subscript on both sides. So the compound is the same on both sides, but magnesium has a 3 subscript on one side, but not on the other side.
Okay. So, but again, PO3 doesn't just have this. It's a unit altogether. That PO3 is one unit, and then it has a 2. The real subscript of the PO3 is a 2.
Oh, when you say unit, that makes sense. So if it was PO 2 on one side and 3 on the other side, you would just mark it down as PO.
Yeah, it would be different in that case. If it was PO3 here and PO2, they're not a unit, right? That's 2 different things. And so then we'd have to break it up.
So magnesium, the unit of magnesium is 1 magnesium on each side.
That's right.
Not 3 magnesium. And then
yeah. And this just tells me how many I have on that one side. And this says there's 1 on this side.
Sorry, I got it. Sorry, everybody.
No, that's all right. No. It's a good question because that's a lot of things that people have trouble with, right?
Yeah, thank you.
And so don't get worried about that. So
I prefer to distract everybody in the chat, not by talking.
Well, I want you to do both if it's important so that we learn. Okay, so, and then the last unit, what is the last unit that's moving?
Chlorine.
CL.
Okay, so we have Cl. Okay. Okay, so how many PO3s do I have on the reactant side?
2,
And on the product side,
1.
how many P small o?
1 on each side.
1,
One on each side. How many Mg do I have on each side?
3.
3 left,
Three and
1
one.
right.
And then how many CLs?
1,
3 left, 2
3,
right.
2.
Okay, is it balanced?
No.
Okay, so what do I need to do to balance it?
Put a 2 in front of the POCl3 on the product side? Or, wait, let me see. I just had it in my head.
Yeah, that works.
That works.
And then
That
put,
works.
put a 3 in front of the magnesium on the right side and a 2 in front of the PO3 on the reactant side. So
Okay,
like 2, 2, 3,
okay, so you're saying you want to put a 2 here,
right?
and then you're saying put a 3 here,
Right.
okay? So then that gives me 3. That would be how many?
6.
6,
And then over here,
6,
and then that means we have 2 here.
yeah,
Is that correct?
right. And then put a 2 in front of the PO3.
Okay. And so, okay. That's it. Piece of cake.
Yeah, I think I get it now.
Okay. And as I said, we could do it the long way, the longer way.
I did it the longer way right now.
Yeah. And it works the same way, right?
Yeah, it
So-
was the same way.
So if we did it the longer way, we just
Dr.
got
Henry, when we're looking at this problem, is there like, because I know, I mean, you've been doing this for years, so obviously you see it, you probably see it instantly. But for us learning, is there like any kind of way that we can look at the problem and kind of decipher what we should attack first to make it simpler for us, or no, not really?
Yeah, no. There is. So the one thing I always try to look at for me when I go through the step, I look at the problem and I see if there are, I'm going to erase the coefficients to make it. See if things are traveling in groups, right? If they're traveling in groups, it makes it a little bit easier, like PO3, right? So we have a PO3 over here and we have a PO3 over here, right? So then that makes it a little bit easier. So I'm going to collectively add those into groups, right? So that's one thing. The other thing is you kind of look at, when we went through that process, we'll do it here. We'll do it in the long way in this case, okay? So I always like to start off with putting the numbers down so that I know what I'm working with. So reactants, I have 2. My product, I have 1. My PO, I have 1, 1. My Mg, I have 3, 1. My Cl, I have 3, 2. My Os, I have 6 3s, right? So I never start off with the ones that are already balanced. These guys are already balanced, so let's leave those alone. And we may have to adjust them later on, but I always start off with the ones that aren't balanced, but then I want to find the ones that have an easy way to balance, So that's my first thing. So then okay, so I know this is 2. So what is an easy way to make this guy balanced? Well, if I put a 2 in front of here, that already gets this guy balanced. Okay. And then that tells me, okay, so now I have and I have to count for everything else. Okay, so now this guy gets off. So now that's 2. This guy is 6. All right, but that kind of works out because this guy is already balanced. So, okay, so then how can I get this? I go to this next. How can I get this so that it'll be right? So if I put a 2 in front of it, that gets this guy balanced. Okay, so let me go through and count up everything again. Okay, so now I got this guy balanced. And, oh, it's looking pretty good so far. So the other place was here. That's totally balanced. Okay, so now what about my Mg? All right, so I have 3 over here. So if I put a 3 in front of here, that gets this balanced. And then I have 6 of these. So, and if I look here, I put a 2 in front of here. That means I already got that 6, which I forgot to account for earlier. So now everything is balanced. So I really only have to worry about like this guy, and everything else seemed to balance itself out. Does that make sense?
You make it look so easy.
It really, I mean, you guys, I think you guys, sometimes what you guys do, you're looking for it to be hard, right? And so because you're looking for it to be hard, you make it harder than what it is. And so you start just putting things in there, you know, you're just like, okay, I'm just gonna put a number in here just to put it in here, you know? But if you just kind of go step by step, take your time, you know, and it tends to balance itself out, you know, at the end. Okay. Or you guys try to do it all in your head. Like I can't do it all in my head. I'm old now. You know, I can't do it anymore. Like I was sitting there when I was making up your test, you know, I made up your test and I'm like, okay. And then I'm like, okay, yeah, I got this. This is good. And then when I was putting in the answers, I could remember half the things that you know, the coefficients. And I'm like, one of them I screwed up majorly, right? It was supposed to be 25 and I put 17. I don't know where in the hell I got 17 from, but that's what I did, you know? So it's like, because I tried to do it all in my head, but if I put it on a piece of paper, I write it out, it becomes clear. And then I just check things off, you know, making sure that I'm actually right at the end. Okay?
Copy.
Okay. So that is, well, we spent more time than I had planned on balancing equations. So, but this is, balancing equations is an essential part of chemistry. If you can't get the equations balanced, you can't hardly do anything else. The next part of it is we're going to be going over nomenclature, Coalinga next week. Well, not next week. Yeah, about next week we'll be hitting it. Nomenclature, and then Harnell, when you guys get back from spring break, we'll be going over nomenclature. Those are the 2 fundamentals of chemistry. If you can't name it, you can't make the equation, right? And so those are going to be things that you really want to sit there and focus on. So if you have kids, at that point, what you want to do is tie them up to watch the Zoom screen so they'll learn it while you're learning it too, and you have them learn it at the same time. Have them help you. So I know that you don't want them to distract you. You want them to be a benefit to you, right? And for some reason, I have a 7-year-old that my girlfriend has a 7-year-old. And so I'll be talking about chemistry and he picks it up like this. And I'm like, okay, so he's picking up these equations like this, where it took me forever to pick up. And it's something about like, it's just a little puzzle to them. And they look at it as like a puzzle.
Sponge brain.
What was that?
Sponge brain. That's what
Exactly.
kids have. They have sponge
Yeah.
for brain.
Yeah. Yeah. So we want to make sure that you guys are going to be sponges as well too, right? Because we want you to suck it up. Okay. Are you guys good? You're feeling a little bit better? And if you need more help, if you guys look on the Canvas shell, on the modules, there's a lot of stuff on there, I know, but we have these little links and they look like little, chains, little chains. They're links to places that I like to go on YouTube. Like I like Melissa Maribel, right? Because I thought she was very attractive. So, and this is when I was single and like anything that I didn't remember, I'd go to her site and look because I'm like, God, she's very attractive. She understands her material and she explains it so that I can understand. And then there's Tyler DeWitt, right? And then so I linked up to him as well too. I'm like, hey, so these are two places that you guys have as options to help you kind of learn the material if you can't figure it out for me, or if you just need that little extra help. And sometimes we just need that little extra help, or hearing it from somebody else, it'll start clicking. So make that extra effort. And the last thing is hit your TAs up, right? That's what they're there for, okay? They're there to help you. Okay. Are we good? Okay, so to get off topic, we need to talk about some Lewis dot structures of compounds. That's what we're trying to build up to. And I know that you guys have these for homework assignments, right? So we've talked about
When's the next homework assignment due?
For Coalinga, it's going to be next week. For Harnell, it's going to be when you guys get back from spring break. The week at the end.
Two that are due today, are you moving those back?
I'm going to give you guys a little more room for that because there are things that we've not gone over on those homework assignments, but we're going to be going over them today, right?
Oh,
and so technically, I could move them back to Friday, but I'm going to give you guys a little bit of leeway. So Coalinga, you guys will have until next week, probably next Tuesday. But then you're going to have one that's going to be Tuesday and then one that's going to be Thursday, okay?
So Dr. Henry, because I know we have 4 and 5, and 4 was due on Wednesday, but 5 it will be due after spring break for Hartnell or tomorrow?
Yes.
Because I know there's some due tomorrow.
So it's going to be due after spring break. So I'm going to give you guys a little leeway. So it's going to be due on that Wednesday. So we'll go over some stuff on Tuesday, but it's going to be due that Wednesday.
Okay.
Could you by any chance get like an email that just has like the dates of the next things that are due for
Yeah,
like
I'll send an email out for you guys.
consolidated? Okay, great.
And then that way I can kind of separate, because the campuses right now we're kind of separating, right? Because again, Harnell is going on vacation next week. And then Coalinga is going the week after, right? So you give me a moment because I have to get it clear as who is going to be where.
Right.
You'll be getting an email from me to tell you what's going to be due. Okay. But anything that's due already, it needs to be due, except I'm giving you guys a couple of more days. That's both groups. I'm giving you guys a couple more days because there's a few people that were struggling with the craft, with the
lab.
The lab. Thank you. With the lab, yes.
So the lab that's due on Labster, is that due tomorrow?
No. The Labster lab is due tomorrow, but the other lab was technically due
yesterday.
Yeah, exactly. It was due yesterday. And so what I'm going to do, I'm going to open I think open, but we count as late. And so I'm not going to count it as late in your regard.
So Dr. Henry, mine shows structure and shape and chemical bonding as both due tomorrow, homework 5 and 6. You said you're moving those back, or those are still due tomorrow?
He's going to send an email out.
I'm going to send an email out. Those are going to be due next week for Coalinga, but for Harnell, you guys are not going to get those due until you guys get back.
Okay, cool. I started them and I didn't really know what was going on.
Well, that's okay. And you know what? And I want you guys, that's the reason why you guys are getting them ahead. I want you to start them because, we're not all learning at the same speed. I don't know if you guys realize that, right? Are you guys all learning exactly at the same speed?
I'm a slow learner.
Yeah. So some of us, it takes a little bit more, right? So if you started, right, your first thing that you guys should be doing, I always looked at my homework. First thing I would do, I'd open up my book and see if I could find a problem just like it. And then see if they did a problem just like it in my book. And then that's before I even went to lecture, because I'm like, okay, I want to try to get this done. And then I don't know if he's going to get to it when I want him to get to it, but I have time right now. So I'm going to make use of that time. And so that's one thing that you guys need to be kind of proactive on. Kind of get ahead. It's okay to get ahead. Open that book. If you don't know it, open the book. The book has examples, right? It can kind of help you out. And then you come in to me, and then if you guys are doing that already, you're already ahead of the game. And you're like, hey, I have this question. Like, for instance, somebody gave me, I think it was C2H2 Cl2, right? And they have this on their Canvas show, right? One of the homeworks that are going to be due here soon, if you haven't already looked at it, okay? And then this is what they're doing, right? They're thinking about it in terms of right now what we know, they're limiting stuff of what we know. So they're saying, okay, so we have a carbon, and then so this is a carbon is going to be attached to this, and this is going to be here, and they're just putting things around like this, right? Cl and H and H. This is what they've done, okay? Where there's only a single center atom. Well, in chemistry, there are certain cases that we're going to have a single center atom, but there are going to be other cases where we're going to have multiple center atoms, right? So if we think about the structure, we've talked about the electron configuration of carbon. Do you guys remember the electron configuration of carbon?
Sure.
Anybody?
Yeah.
Okay.
Ready for it? You want it?
So just for kicks and giggles,
Helium.
the electron configuration for carbon is you said helium.
And then it is 2s2. And then 2p2.
Okay. How many valence electrons does carbon have?
4.
It has 4 valence electrons. So if I was drawing this Lewis dot structure, what would I do?
The like little dots.
Yep, the
4
little dots. Lewis dot structure. Yep.
4 of
You
them.
Would you have
also,
4 dots, 2 on one side, 2 on the other?
I would just have 4 dots. We don't have to say where it's at, right? Okay. So I'm just going to put my 4 dots, right? Because those dots represent valence electrons, right?
Mhm.
And that's what we were learning the last time, right? Okay, so we kind of talked about, and we're getting ahead of the game here a little bit. We've kind of talked about these valence electrons. Well, valence electrons are just the electrons that we can use to try to reach our octet. So the goal of chemical compounds form so that they can be more stable. That is the reason why you'd want to try to form a chemical compound, either an ionic compound or a chemical compound, okay? Or a covalent compound, sorry. Okay, and we're going to talk about that here right now. Let me pull up some slides. Yeah, 15 minutes. This is taking a lot longer than I wanted to. But my point is here, right? So she's already started this problem. She's already thinking about it. But we think about it in terms of what we know right now, right? And so sometimes we've got to pick up a little bit more. So we got to get a little bit ahead. And that's what I want you guys to be comfortable getting a little bit ahead. So we talked about Lewis structures. So we're going to go and take a look at our P table, and then we're going to get back on track. Let's see, P table right here. Can you guys see my P table?
No.
What do you guys see? Do you see it now?
Yes.
Okay, and it looks weird because we were talking about another thing in class. Let's see if I can get it back where it's supposed to be. Okay. So do you guys see the beautiful P table there? Okay, so if I'm
Yes.
Lewis structures for, we said carbon, right? We already know what carbon looks like. Carbon has 1, 2, 3, 4. So it'll basically have 4 dots. Okay. What about aluminum? Al.
It'll have 3 dots.
3.
It'll have 3 dots. 1, 2, 3. Okay. What about S?
6.
6.
1, 2, 3, 4, 5, 6. Okay. What about Cl?
Would that have 7?
That'll have 7.
Wait, real quick, what determines how many they have again?
The number of valence electrons that they have, right? So really, I'll give you a hint. If you look at the S and the P. This is the easiest way of doing it. S and P. And then you just count the level that they're at. So Cl is right here. This is where Cl is located. So I just count 1, 2, 3, 4, 5, 6, 7. That's how many dots it's gonna have.
You
Okay.
understand?
about-
You understand why he said valence though, right? Because the core is gonna be the purple ones. Can't think of what they're called.
Noble gases.
Noble gases.
Yeah.
Okay,
That's why
so
we don't have those.
so the I, how many valence electrons does that have? If you just count the S
7.
and the P, it's 7. So all of the ones in group 17, right here, all of these guys are going to have 7 valence electrons.
Wait, I got a question.
Yep.
Does that trick still work once you get down into the 3D table?
So when we're starting to talk about these guys, right, that trick doesn't work.
Right. So it only works for.
It only works for the stuff that's in the elements that are in the P and the S.
But like
or
if
in
you
the
go down on
group.
like period 5.
Yeah,
And-
even period 5, right? Because isn't
Oh, so
iodine in period 5?
you can just skip the 3D table then?
Yeah, because it's full, right? Because
Oh.
over here we've already filled it up, and that's considered full, so it's happy. So we're not going to mess with it.
Okay.
So then the only thing that we're going to have to be able to use is just those that are in this orbital, in the S and in the P.
So those still exist there, but they're already balanced or whatever. They're already filled
Yeah,
up.
yeah, they're already filled up. So they're kind of locked up in a vault that you don't want to, right?
It's kind of like the noble gas or whatever, where it's already reached like balance. Or,
Exactly. Yeah. Yeah. So once the D shell is completely full, it is kind of like it's one of the noble gases, right? Kind of like what we did with the noble gas. Yeah.
it's all coming together.
Okay. So questions, concerns, Cash. You feeling pretty good about that? So one more. Beryllium, Br. I mean, not Br, Be.
2.
Okay. Simple.
Can you just put the dots anywhere around it, or do they have to be on a specific side?
Well, you can really, right now, because it's not the active thing, you can put it anywhere around it. But usually I like to make them balanced, or I'll put them both up here, or sometimes I'll do this because I know it's going to react with something. You know, I'll put it on
The same thing.
each side. As long as there's 2 around it, it really doesn't matter. Nobody should dock you for it.
Okay.
Okay. But usually we don't do anything like this. Let's say for carbon, we won't put them all 4 on one side like this. We usually want to balance it out because it looks weird. Okay.
What about for silicon, Dr. Henry?
Can you tell me?
Like,
Look
what
down.
if does it matter if the dots go 2 on the right and another 2 on the left side, or it has to be from on the
No.
top?
We could have put 2 on the right and 2 on the left. That'd have been
Oh,
fine.
okay. Now I get it.
Okay. So those are valence electrons, but that's the use of the Lewis dot structure. Okay. So if I had something like this, let's see. Okay, so now that you guys are kind of familiar with that, and you guys kind of have a good understanding of it, you feeling comfortable?
Yeah.
Okay, good. Okay, so now we're going to talk a little bit about trends, right? So the trend is we're going to talk about atomic size. As we move from left to right, our atomic size is going to get smaller. So hydrogen is going to be bigger than helium. And then if we go down this row on the second period, lithium is going to be bigger than beryllium. And then fluorine is going to be like the tiny one. All these guys are going to be bigger. So lithium is going to be bigger than fluorine. So as we move from left to right, it's going to get smaller. Okay. As we move from top to bottom, smaller up here. And that's smaller in size, so the radius of the atom. As we move from top to bottom, it's going to get bigger. So we've kind of talked about this. Remember we were talking about, what was that?
In our first lab, sir, we had to like explain this as one of the answers.
See, that's good. So you guys have already done this already, right? So
Not really, but just answering the question in lobster.
So remember, it's kind of like the Russian dolls, right? Where we have the little doll in the middle,
Nesting
the
dolls.
bigger doll, then the bigger doll, and the bigger doll. So what we're doing as we go down, these guys are just going to get bigger, right? So knowing that, who's going to be the biggest? Who we expect to be the biggest atom, and who we expect to be the smallest atom?
Lorandom.
The one on the bottom left would be the biggest.
Well,
So
and
francium?
largest. Yeah.
Okay, so this guy would be our biggest.
Francium.
Okay, and who would be the smallest?
Helium.
That's right. Okay, so looking at the periodic table kind of helps us understand that too. And the reason why this is the case is because it has a lot to do with that charge, right? The charges and the layers of electrons, right? So helium has 2 protons in the middle. So it has 2 electrons, and it's pulling those electrons really, really tight. So the more positive charge that we have in the middle, the tighter we're going to be pulling. Okay, so this guy has 2, but then you have to think about it, right? Remember, it's like the dolls. So if you have another layer of electrons, well, that positive charge is in the middle. It's not going to be as effective because you have another layer. So this guy, neon, is going to be bigger than helium, right? And then we have another layer, right? Then argon is going to be bigger than neon. Does that make sense?
Yes.
Yes.
Okay.
Dr. Henry, you know how you're saying that from the left to right, you said the atomic mass, the atomic radius is larger?
Yep.
So that has nothing. Okay, no, never mind. I was gonna ask about like it in comparison to its like actual atomic mass, but on the actual table, but never mind.
Okay, so the next thing is there's this thing called ionization energy. Well, now, okay, so before we do that, let's ask a question. Okay, so now you guys know that. Here's my question. I have a lot of notes. So if I miss a question from the chats, can you guys help me out?
Sure.
Sometimes I look up and then there's like 50 chats and I'm like, hey, did I miss something?
Most of it's probably not important.
It's Nate
It's
talking about
Nate.
It's Nate.
gangs and tattoos.
Okay, so referring to the atomic table or the periodic table and the list of atomic numbers 15, 16, and 33. Let's see, refer to the atomic table and list the atomic numbers 15, 16, and 33 in order of increasing atomic size.
I would
you want to
start
tell
off
you?
with 16, then 15, and then 33.
I would do 33, 16, and then 15.
Wait, it's going from the lowest to the biggest, right?
So we're
It's a sort of increasing.
we're talking about atomic size increasing. So we're going from the smallest to the biggest. So who's going to be the biggest and who's going to be the smallest? Okay, so let's.
Right. So wouldn't 33 be the biggest?
Okay, so wait, hold on. Can you guys? Let's see. Do you see my periodic table? No. Oops, I don't see my periodic table.
No.
Let's see. Let me pull it up. Give me a second. There we go. So we said atomic number is 15. So what is 15?
Phosphorus.
Phosphorus.
Phos-
16
That's
Sulfur.
sulfur.
and 33.
Arsenic.
Arsenic.
Okay, so who's going to be the smallest?
That would be
The
sulfur.
smallest is gonna be 16 sulfur.
So it'll be 16. And then,
The medium will be 15.
okay, and then the biggest,
Will be 33.
Okay.
Right?
that's right. Piece of cake. So
Yeah.
it will be sulfur, phosphorus, and then arsenic. Okay. Let's see. The next thing that we're going to talk about is called ionization energy. Ionization energy is the energy that is associated with removing an electron. So you're going to remove an electron. So the first ionization energy is removing one electron. The second ionization energy is removing 2 electrons. The third ionization energy is removing 3 electrons. Okay. So, and I'll type that up for you. Ionization energy. Okay. So we were looking at ionization energy earlier. That's what I was showing you guys earlier in another class. So the first ionization energy is here. So let me click on it. If you actually click on P table, come on now. There we go. Can you guys see the change?
Yeah.
Okay, so this is the ionization energy. Now, this is the general trend. Now, there are always going to be exceptions. There's always going to be that one guy who's got to have to be, I'm different, right? Always. So in this case, that guy is always going to be a nitrogen. Nitrogen is always going to be different. A little difficult all the time. And if you actually take a look at nitrogen, look at the value of it, it's actually, it has a higher ionization energy than oxygen, okay? So, and you can kind of tell by the color. But as we move from left to right, the ionization energy is going to increase, meaning that the energy that it's going to take to try to remove an electron. Now, these guys over here aren't going to want to lose an electron. They want to gain electrons. So their ionization energy is going to be really high. The noble gases are going to be the highest, right? So if you kind of take a look, helium has a really high value because it does not want to lose an electron. It's like, no, I'm happy, right? I'm happy you are not taking my electron. Where these guys are going to have lower ionization energy because they want to lose electrons. And if you actually take a look, francium technically should have the lowest. It's a little bit of an exception. Cesium is a little bit lower than francium. So ionization energy is going to increase from left to right. Or at least the first ionization energy is going to increase from left to right. And then it's going to decrease from top to bottom. Now, these trends are kind of important, right? And it's the periodic table kind of sets it up so that we can kind of understand these trends, right? We notice that these guys have very low ionization energy relative to these guys over here, right? So we see that increase happening. Okay. Again, there's always going to be exceptions, right? And when you get here in the middle with the transitional metals, again, pretty much ionization energy is going to increase, but then you get back over here, it switches back over. There's that whole concept of orbitals being filled. So, okay. Are you guys with me? But
Yeah.
General trends, that's what we're going to be talking about. Okay. And let me show you. Okay, so let me clear. Okay, so we kind of talked about what ionization energy is, and then So just that concept of removing an electron. And again, this is just showing you that general trend. Okay, there's hydrogen, and helium is really high. And then we have lithium, beryllium, boron, chlorine. So you have these guys that are exceptions, right? So we have beryllium, that's an exception. But you guys can see it increases as we go from left to right. So generally it's going to increase when we go from left to right. Now, when we start talking about the second ionization, so second ionization energy is saying, okay, so now we're looking at the energy to remove the first one's already gone, and now we're removing that second, right? So it already has a +1 charge, and now you're going to remove another electron with it, right? Now that's going to change how things are going to behave, right? First ionization energy is going to increase as we go from left to right, and then it's going to decrease as we go from top to bottom, right? Second ionization energy, well, it depends on who you are, right? Whether your second ionization energy is going to increase, right? In certain cases, these guys are just going to get bigger. The ones that don't want to lose electrons, they're just going to get out of control. Okay, so here's the second ionization energy, right? So relative to our first ionization energy, here's our second ionization energy. So these numbers get bigger, right? But still, that trend still kind of lies the same. But then you get these guys like lithium. Lithium already lost its first electron. It's not going to want to lose anymore. Where beryllium is like, okay, I'm cool with losing one more. Let's go. Let's do it, right? All of these guys, they've already lost that one for that second ionization energy. They're not going to be willing to lose that second one, okay? And ionization. Okay, so knowing that, can we put these guys in order for the increasing order for first ionization energy? Beryllium, nitrogen, fluorine. What would be the order? You guys need to see the periodic table?
You want it from highest or increasing? So from lowest going to highest?
That's correct.
Okay, so lowest francium. Okay, where's your letters at?
So it's beryllium, it's B.
Beryllium, francium, and then it
No,
was
it's beryllium, nitrogen, and fluorine. F is fluorine.
Oh, let me see. All right, so
Yeah.
beryllium, nitrogen, and fluorine.
Yeah.
Would it be in that order?
It would be exactly in that order.
Yeah.
Yeah. So it's going from left to right. So beryllium is right here. Beryllium, nitrogen, and fluorine. Beryllium will be the lowest, nitrogen would be in the middle, and then fluorine would be the greatest.
We had these in the homework, chapter 4. Or homework 4.
Okay. So the last thing that I want to talk about, I know we're over. Sorry to keep you, but I'm trying to get as much stuff in as I can.
It's cool.
Okay. So the last couple of things that I want to talk about is the chemical families, right? So those groups are chemical families. So those groups, the alkali metals, those guys are going to behave very much alike. They're going to be reactive, right? So they're going to want to react with water. They're going to want to react with the air. They're going to be reactive. That's just their nature, right? So all of those guys are going to kind of behave similar, right? So we'd expect them to kind of react very similar. Okay. Okay, then in the case of the halogens are all in the same, they're going to be very similar. They're also going to be very reactive, right? So then they're going to be quick to react to things. They're going to be kind of explosive when they do react. And so those are the things that we do. So we have the periodic table organized in terms of the family, how they behave, where they're, how many valence electrons that they have, stuff like that. So that's going to be very important for us to kind of pay attention. Okay. So if I ask you a question like, so which element would behave just like oxygen or similar to oxygen? What would you guys say?
Nitrogen?
Nitrogen?
That would behave similar to it? Oh,
similar to oxygen.
sorry, sulfur.
Sulfur, yes. So we would say sulfur because sulfur is in the same group as oxygen. Okay?
Chalcogen. How do you say that? Chalcogen.
So it's chalcogens. So we have
Chalcogen.
our chalcogens, and then we have our netogens, and then we have our halogens. Okay. Okay, so this is just helping us understand that. And P-table does a beautiful job of showing the different groups, right? You can even highlight them and it'll just highlight those, okay? And so you need to be familiar with those groups and then familiar with the ones that are going to behave the same, right? Questions, concerns, Cash. Okay. The other thing is that we know that group 1 always has 1 valence electron. Group 2 always has 2 valence electrons. Group 17 has how many valence electrons?
7.
7.
7, okay? And so you want to kind of put that to memory because it makes it a little bit easier for you guys to sit there and work through the problems. Okay? And then we know that we have the noble gases, right? Noble gases are noble, right?
Yeah, they're better than everybody.
They're better than everyone. And so their octet is full. So technically they have 8 valence electrons and they're super cool, right? And they don't want to react, unless they absolutely must react. And they're
Like
usually forced to do that.
The sophisticated people.
Exactly. They're high class. Okay. So, and you want to be able to distinguish between metals and non-metals, right? We know that all of these guys here, oops, I got carried away. So all of these guys here are all metals. All of these guys over here are non-metals. And then we know what metalloids are. Metalloids they have characteristics of both metals and non-metals. Okay. And then in terms of metallic characteristics, well, as you go from right to left, you're going to become more and more metal-like, right? So we'd assume these guys are more metallic than guys in the middle, right? So if we talk about metallic characteristics, the alkali metals are the most metal-like, and then the stuff over here is less metal-like. And that makes sense because we know that these guys are non-metals, so we know that they're not going to be too much metallic-like, right? But as we move across, it becomes more metallic, the characteristics do, okay? Questions, concerns, Cash? This is just basically a summary of everything that we've talked about at this point, things that you want to try to keep in mind. So your metals are basically, they are going to have 1, 2, or 3 valence electrons, right? And sometimes they could have, 1, 2, or 3 valence electrons. Our non-metals are going to have 4 or more valence electrons.
I have a question.
Yep.
What is 109, 110, 111, 113, 15, 116, 117, and 118 considered?
So you said 109, these guys?
110. Pretty much, yeah.
Okay.
Besides 112
So-
and 114.
So all of these guys are the reason why they're in gray is because tentatively they haven't been shown to be completely stable, so that they don't stay in existence very long. But these guys are more than likely, if you look at the general trend of the periodic table, once we figure out a way of keeping them stable long enough, these guys are all going to be pretty much metals. So these guys will probably all be metals. This guy may be a metal or a metalloid, because if you look at here, the trend right now, we have this nice little trend going on. So I'd assume that this guy would either be a metal or a metalloid based upon the general trend. And then this guy is probably going to be where it's located, either a metal, it's going to be a metalloid, or it's going to be a noble gas, or may have characteristics of both.
Okay.
Okay. So, but then that's just, it's an educated guess. We don't know yet because those guys have not been stable enough for us to determine.
Okay.
Okay. Okay. So I have 2 slides left. So These are characteristics of metals and characteristics of nonmetals. Metals are always going to be malleable. They're going to be able to conduct electricity. They're going to have high thermal conductivity. They're going to be ductile, right? So we can draw down the wires. So we can put that out. Where nonmetals are going to be brittle. They're going to be non-ductile. They're going to conduct. They're going to be poor thermal conductive. So, you know, we use silicone as a way of kind of protecting ourselves, and we use carbon all the time, like in terms of plastics, right, for insulation. So those are examples that nonmetals don't conduct electricity very well. Okay. And so we want to pay attention to those characteristics and try to keep those in mind. And come on now. So this is just showing you that table, basically P table. This is just showing you the metallic trends. So you become more metallic as you go down and as you go across from right to left. Okay, and that's it.